Welcome to The Deep Dive, the show where we take the impenetrable foundations of the internet and, well, try to transform them into crucial, understandable knowledge. Today, we are plumbing the depths of OpenSSL.
OpenSSL. Yeah, you could definitely argue it's the most critical piece of invisible open source software out there supporting modern communication. If you see that padlock in your browser, right, or your email's encrypted, your secure file transfer just works, well, chances are OpenSSL is providing the underlying TLS and SSL protocols making that happen. We really only think about it when something goes badly wrong.
And its history is absolutely defined by those near catastrophic failures. I mean, I remember the whole security industry just holding its breath back on November 1st, 2022, waiting for that critical vulnerability alert. Everyone thought it could be the next Heartbleed.
Mm-hmm.
And now the challenge isn't just, patching old issues. It's this existential threat quantum computing is forcing this seismic shift, pushing OpenSSL developers to build crypto agility right into the foundation.
Yeah. Well, what's fascinating really is how OpenSSL is kind of forced into being the bellwether for the entire security world, because it is everywhere. It's embedded in web servers, OS components, appliances, you name it. So when the OpenSSL team releases a big new version with a major feature, like this post-quantum cryptography stuff, the rest of the world basically has to follow, and pretty quickly, too. It really sets the pace for global migration.
Okay, so our mission today is to give you, the learner, a shortcut to understanding this vital toolkit. We're going to unpack OpenSSL's architecture, look at that revolutionary change from engines to providers.
Right.
Then we'll look back at some critical, high-stakes lessons learned from the really damaging vulnerabilities. Heartbleed, of course.
Oh, yeah.
And that Debian weak key mess.
That was a bad one.
And finally, we'll analyze the future of security. That huge pivot to built-in post-quantum cryptography, PQC, which is the big news in OpenSSL 3.5. Okay, let's unpack this invisible foundation then. When most of us talk about OpenSSL, we probably think of the command line tool, right?
Yeah, usually.
But the architecture is actually more like a set of libraries working together.
Yeah.
A multi-tool setup. You mentioned 3 primary pillars.
That's a really key distinction, yeah. The command line tool is just like the tip of the iceberg. At the heart of it all are 2 core libraries. First, there's LibreSSL.
Okay.
This library is totally dedicated to implementing the secure protocols themselves. We're talking TLS 1.3, DTLS 1.2, and the newer stuff like QUIC version 1.
RFC 9000.
Exactly. It doesn't do the actual crypto math, though. It just orchestrates the process. It manages the TLS state machine, makes sure the handshake sequence is right, handles certificate validation, manages the session lifecycle, that kind of thing.
So LibreSSL is the protocol manager sitting on top of the real powerhouse, which must be libcrypto.
Precisely. libcrypto is the general-purpose cryptographic core. It's the engine room, It's got all the number crunching implementations. If libcrypto needs to do, say, an ECDHE key exchange or verify a signature, it calls down to libcrypto. This library has everything hashing functions like SHA-256, those complex BIGMEM routines for large number math, and crucially, managing cryptographic randomness properly. It's the full-strength toolkit that really defines the security of anything relying on OpenSSL.
And then the third pillar, that's the executable itself, the OpenSSL command line tool.
Right, that's the utility layer. It's the developer's Swiss Army knife, as people call it. Professionals use it constantly, generating certificate signing requests, CSRs, inspecting private keys, checking certificate chains, diagnosing connection issues. Like, you can use this client command to simulate a handshake and figure out why cipher negotiation is failing.
Right.
Or use GGSD to compute a specific hash. It's essential for ops and dev work.
And because it's so versatile, OpenSSL's use cases are just staggering.
They really are. It secures practically all major web servers, Apache with Modcyan, Nginx, HTTPS configs. It's fundamental to PKI, public key infrastructure, and managing certificates. It's the backbone for secure tunnels, like with OpenVPN. And because it's open source and so feature-rich, you find lightweight versions compiled directly into embedded devices, IoT platforms, which makes it critical for compliance, too, in sectors like finance, government, healthcare, anywhere you need to meet specific standards across all your network stuff.
But securing all these different complex environments that needed a major architectural cleanup, that came with OpenSSL 3.0, right? The shift from the old engine system to this modular provider concept. So what really pushed them to make this change?
Well, the move to providers was critical. It was driven by needing more modularity, being ways to handle compliance, and honestly, just better security control. Before 3.0, you had this engine API. It was used to extend libcrypto. Developers could use it to hook in custom hardware accelerators or maybe unique algorithms.
So where was the security risk with that old engine system? It sounds flexible.
It was flexible, but the risk was in how much low-level control it gave. There were functions like EVPP key meth new that let developers create or modify these custom methods. They could basically inject functionality way down deep in the crypto core. And if that wasn't handled absolutely perfectly, it could easily bypass all the higher level controls, things like algorithm selection policies, key rules, secure configurations. It created this risk where an admin thought they were running a secure setup, but some low-level engine modification was actually bypassing the intended provider and maybe using insecure code or weak algorithms. Because it was so complex and risky, those old engine APIs are now deprecated. Authors of external crypto modules are really encouraged to switch over, refactor using the newer, cleaner provider API.
Okay, so providers are like these self-contained modules for crypto algorithms. They give you a much clearer view of what's actually being used. Tell us about the key providers that came with 3.0. They define the new landscape, right?
Right. There are basically 4 key providers you need to understand. First, the default provider. This is your standard operational core. It has all the normal built-in OpenSSL algorithms that are considered modern and safe. If your application doesn't specify anything else, this is what gets loaded. Standard crypto functions, ready to go.
Simple enough.
Second, the FIPS provider. This one's crucial for places needing strict government or regulatory compliance. It contains only a very carefully selected subset of algorithms specifically, the ones that conform to standards like FIPS 142 validation. This lets organizations isolate and guarantee their crypto compliance. It makes sure non-compliant algorithms just can't be picked by accident.
Yeah, that must make compliance audits way easier. That's a huge administrative headache usually.
Absolutely. Huge reduction in burden there. Then you've got the base provider. This one's simple but essential. It just contains a small set of necessary non-cryptographic algorithms. Things used for like encoding and decoding keys to files, basic utility stuff. So if you load the FIPS provider, but you explicitly don't load the default provider,
Right.
you still need the base provider to handle those fundamental non-secret tasks.
Okay. And finally, the one that sounds most important for forcing security upgrades, the legacy provider.
The legacy provider is where OpenSSL really drew a line in the sand on security. It houses all the algorithms now considered obsolete, insecure, or just strongly discouraged. We're talking relics like MD2, MD4, DES, RC4, RC5, IDEA, Blowfish, Cassie5. A lot of these, like RC4, were everywhere once, but they're totally broken now.
And the revolutionary part of the 3.0 architecture with this provider.
So the legacy provider is not loaded by default. This was a massive, deliberate design choice. In the past, backward compatibility meant OpenSSL would happily use RC4 if some old client requested it. Now, to enable any of those older, weaker ciphers, which, okay, might still be needed by some ancient enterprise app or legacy appliance somewhere.
Right, happens all the time.
You have to explicitly configure OpenSSL to load the legacy provider. This design completely flips the script. It ensures the default out-of-the-box configuration is modern, strong, and secure. It forces admins to consciously accept the risk if they choose to enable older crypto.
Looking at OpenSSL, it feels like its ubiquity is also its greatest weakness when a vulnerability hits.
Yeah.
It's not just a bug in one product, it's like a global infrastructure emergency. And because OpenSSL can be statically linked, meaning its code gets compiled right into some third-party app or device.
Right, baked in.
Finding every vulnerable instance is often just impossible unless you have a really comprehensive software bill of materials and SPON.
Exactly. And that fragility means organizations can spend weeks just chasing down every appliance, every bit of custom code that might have a vulnerable version hiding inside. That difficulty is what made things like those X.509 buffer overflow alerts in 2022 so terrifying. Their response was this mass kind of chaotic global patching effort, mostly because nobody really knows exactly where all the copies of OpenSSL actually live.
Okay, let's start with the big one, the one that really defined this era of open source vulnerability management. Heartbleed, CVE 2014-0160. What made this seemingly simple bounds checking bug so utterly catastrophic?
Heartbleed was just an astonishing failure in validating input data. It was in the TLS Heartbeat extension. The extension itself was designed for, like, liveness checking, just sending a small message to confirm the secure connection was still active without needing a full, expensive rehandshake.
And the attack mechanism was chillingly simple, wasn't it?
Yeah, terrifyingly simple.
Yeah.
It hinged on a failure to properly check the length field that the attacker provided. An attacker could send a heartbeat request claiming the payload was, say, 64 kilobytes long.
Okay.
But only actually send like a single byte of data.
Okay.
Because the system trusted that attacker-supplied length and allocated a 64 KB buffer, the server would read the real data, the 1 byte, and then just happily grab the next 64 KB of whatever was adjacent in the server's memory heap.
Wow.
And send it back as the response.
And that memory scrape could pull literally anything from the server's running process.
Exactly. This wasn't just leaking harmless debug info. It could leak the server's long-term private keys.
Game over.
Yeah, total game over. That meant an attacker could retroactively decrypt all the past communications they might have stored. It could leak session tokens, letting them hijack active sessions, expose usernames, passwords, anything that happened to be in memory. The incident caused immediate, widespread panic. The key lesson learned was twofold, really. First, the absolute necessity of rigorous input bounds checking, especially in security-critical code. And second, the strategic importance, the necessity of perfect forward secrecy, PFS.
Heartbleed really cemented PFS as a global requirement, didn't it? How did PFS help mitigate that kind of damage?
PFS makes sure that for every single session, a unique, temporary, ephemeral key is generated, usually using algorithms like ECDHE. So even if the server's long-term static private key was compromised by something like Heartbleed, those ephemeral session keys used for each connection are destroyed right after the session ends. So the attacker can't use the stolen static key to go back and decrypt past traffic they might have recorded. If a key gets compromised, PFS limits the damage to just that current ephemeral session. It prevents that wholesale retroactive decryption of potentially years of stored data.
Okay, shifting gears to a different kind of failure. That Debian weak key generation flaw from 2008, CDE 2008-0166. This one really highlights the danger lurking in the supply chain, even when the original code itself is fine.
Oh, this was a spectacular and, frankly, embarrassing failure. And it was caused purely by a vendor modification. Between 2006 and 2008, a patch was applied by a Debian maintainer to the OpenSSL package distributed with Debian-based systems like Ubuntu. The patch was actually meant to do something simple, just silence a non-critical warning from a code analysis tool about potentially uninitialized data being used somewhere. But in trying to clean up the code to stop the warning,
oh no,
the maintainer inadvertently removed the crucial lines of code that were responsible for gathering enough entropy, enough true randomness, to properly seed the pseudo-random number generator, the PRNG.
So their random numbers weren't random at all?
Not even close. They were generated using this highly limited set of seed values based mainly on things like the process ID, which is predictable, the result. Any keys generated on those affected systems, SSL/TLS certificates, SSH keys, VPN keys, whatever, were incredibly predictable. You could basically guess them through brute force because the pool of possible keys was tiny. Thousands, maybe hundreds of thousands of server identities across the internet were instantly worthless.
Wow.
The big lesson there was that security requires trust through the entire software supply chain. Vendor patches, even seemingly harmless cleanup efforts, can introduce massive systemic risk. You need rigorous auditing, even outside the core project itself.
Okay, let's move to more recent history. We had those X.509 buffer overflows, CVE 2022-3786, and CVE 2022-3602 in OpenSSL 3.0.x. Now, the severity was eventually downgraded slightly from critical, but they still caused serious alarm, right?
They did. And they really highlighted this persistent, almost structural security risk that comes with parsing complex old data formats. X.509 certificates are the standard for web identity, right? They rely heavily on ASN byte 1 encoding, which is deeply nested, incredibly intricate, and frankly, a bit of a mess to parse safely. Anytime you have code parsing these complex, decades-old structures, especially when they're coming from untrusted network sources, you're creating a potential attack surface. These two vulnerabilities were high-severity buffer overflows found right in the code that parsed those certificate structures.
And these incidents tied directly back to that operational headache you mentioned earlier, just finding all the vulnerable copies.
Precisely. That 2022 incident really hammered home the idea that just running apt upgrade or patching your main OS OpenSSL isn't enough. Not even close. Organizations absolutely must have a way, ideally using an accurate SBOM, to quickly find and patch every single instance of the library, especially the ones buried deep inside third-party appliances, network gear, or custom apps where OpenSSL was statically linked right into the executable. You have to hunt them all down.
So we've established OpenSSL is constantly fighting fires from past vulnerabilities, but now it's facing this threat that isn't just theoretical anymore. It feels inevitable: quantum computing. We need to define Q-Day, that point when a functional, cryptographically relevant quantum computer, a CRQC, can actually break our current public key crypto. Understanding that is key to seeing the urgency here.
Yeah, the urgency is entirely practical. We're operating under the shadow of store now, decrypt later attacks. Yeah. Sophisticated adversaries think nation-states know it takes a long time to build these quantum computers. So right now, they're likely harvesting huge amounts of today's encrypted data, just vacuuming it up and storing it. Knowing that once Q-Day arrives, Shore's algorithm running on a CRQC will let them instantly break the standard RSA and elliptic curve crypto used to protect those secrets today. And since history shows us that major crypto transitions like moving from DES to AES can take, 10 to 20 years.
Right? A long time.
We absolutely have to start migrating the infrastructure today. We can't wait.
And NIST, the U.S. National Institute of Standards and Technology, they've provided the concrete roadmap that's pushing the industry forward now.
Yeah, NIST has been running this big multi-year competition to standardize quantum-resistant algorithms, and their deadlines are basically non-negotiable mandates for many sectors. Right now, between now and 2030, the security world is supposed to be evaluating, testing, and starting the real phase-out of existing crypto, replacing it with these new quantum-resistant algorithms. And the final target is crystal clear. By 2035, a full transition is required. Vulnerable, outdated encryption methods will be fully deprecated, certainly across government and regulated systems. OpenSSL 3.5 is the direct response to that mandated timeline.
Which brings us right to OpenSSL 3.5. The absolute headline feature is that built-in native support for NIST's finalized post-quantum cryptography standards.
This was a monumental engineering effort, make no mistake. OpenSSL 3.5 incorporates the algorithms that correspond exactly to those NIST standards, FIPS 203, 204, 205. They're making them first-class citizens right alongside RSA and ECC. Specifically, they've integrated MLChem, that's Module Lattice Key Encapsulation Mechanism, which you might know as Kyber from the competition. That's for key exchange.
Okay, Kyber. Got it.
Then MLDSA, Module Lattice Digital Signature Algorithm, or DiLithium, that's for general digital signatures.
DiLithium for signatures.
And finally, SLHDSA, Stateless Hash Digital Signature Algorithm, better known as SCSCS plus SAY. That's a different beast, a hash-based signature scheme, very robust.
Okay, let's ground this technically for a second. What's the fundamental difference in the security assumption between our old standards, like RSA, ECC, and these new lattice-based schemes like Kyber and DiLithium?
Right, that's the core of PQC. Classical crypto, like RSA, relies on the difficulty of factoring huge numbers into primes. Shore's quantum algorithm just eats that problem for breakfast. Lattice-based cryptography, which MLChem and MLDSA use, is based on the difficulty of solving different math problems. Problems related to finding the shortest vector in a high-dimensional grid, or lattice. This is believed to be a fundamentally different kind of hard problem that even a powerful quantum computer can't solve efficiently. That's where the quantum resistance comes from.
So developers using 3.5 can now just generate quantum-resistant key pairs and negotiate PQC key exchange right out of the box.
Yes, exactly. But the standard setting, the default, is actually this really interesting hybrid defense strategy.
The hybrid mode.
Yeah, it's the recommended kind of risk-averse way to transition. And OpenSSL 3.5 makes it the default for TLS 1.3. The specific cipher suite is X25519 plus MLKU 768.
Okay, walk us through what that combination actually achieves for the listener. Why combine them?
So the hybrid approach is all about maximizing resilience during this transition. The connection combines two totally different algorithms for establishing the key. X25519 is our well-known, widely deployed classical elliptic curve algorithm, strong against classical computers.
Right.
MLChem 768 is the quantum-safe Kyber 768, specifically NIST's Level 3 security standard for PQC key exchange. The final session key that encrypts your data is derived in a way that relies on the security of both of those underlying key exchanges.
Oh, okay. So if one breaks.
Exactly. If a classical attacker somehow breaks X25519 today, the key derived from MLChem 768 still keeps the session secure. Conversely, if sometime in the future a quantum computer breaks MLChem, The connection remains protected by X2555519 against classical attacks until Q-Day actually arrives. It's a really prudent hedging strategy. It protects against both immediate classical compromise and the looming quantum threat simultaneously.
Smart. Okay, so we have those two quantum-safe signature schemes, MLDSA, dilithium, and SLH-DSA, S-fins, ETH S+. You mentioned they serve different roles based on performance. Dilithium is lattice-based, generally faster, so why even bother with SYN-CS plus A?
Yeah, it comes down to this trade-off between ultimate security assurance and practical usability. MLDSA, dilithium, being lattice-based, generally offers smaller keys and faster signing operations. That makes it suitable for high-volume stuff like web server certificates or code signing where speed really matters.
Right.
SLH-DSA, SYN-NCS plus key A is hash-based. Its security relies only on the strength of cryptographic hash functions like SHA-256 or SHA-3. That's an extremely strong, very well understood security assumption, completely independent of those lattice problems that Kyber and dilithium rely on, gives you diversity in your assumptions.
But SYN-CS Plus comes with a huge practical cost, doesn't it? I read that signatures can be massive, like 8 KB up to 40 KB, and signing is really slow. Isn't that totally unworkable for, say, high-traffic websites or resource-constrained IoT devices? Is that security trade-off really worth the latency hit?
That's a fantastic question, and you're absolutely right. For low-latency TLS handshakes on, say, a busy web server or a tiny embedded device, no, SVS Plus is generally impractical. However, it's ideally suited for highly sensitive, low-volume, archival uses. Think about root certificate authority certificates, or maybe key infrastructure components that need to remain secure for decades, many decades.
That's long-term stuff.
Exactly. If a root CA certificate needs to be valid in, say, 2050, its signature needs the most robust, most conservative defense possible. The large size and slowness are acceptable in that specific high-assurance context because the security guarantee is so strong. It's a hedge, even if future breakthroughs were to find flaws in lattice schemes.
Okay, one last thing on this quantum transition. There's always the threat that emerges during these shifts. It's downgrade attack. If an attacker messes with the handshake to strip out the PQC options, trying to force a weaker fallback to just classical crypto, how does OpenSSL 3.5 help mitigate that?
All right, the mitigation here relies entirely on using modern protocols. An attacker might try to intercept the handshake messages, maybe remove the PQC algorithms from the client's list of supported ciphers. However, if you are running TLS 1.3, which OpenSSL 3.5 strongly encourages, the protocol itself includes robust built-in integrity checks that cover the entire sequence of handshake messages. If an attacker tampers with that chosen algorithm list or tries to force a downgrade, that integrity check will fail. The connection just gets instantly terminated.
So TLS 1.3 itself protects against that tampering.
Precisely. It emphasizes why migrating to TLS 1.3 isn't just about speed or new features. It's essential for these kinds of protocol-level security guarantees, too.
Okay, so moving from the big quantum threat down to operational reality today. The first line of defense is always making sure systems are configured to use the latest, strongest protocols, which means prioritizing TLS 1.3 wherever possible.
Absolutely. TLS 1.3 isn't just an update. It's really a paradigm shift for security engineering. It inherently mandates and enforces perfect forward secrecy. No choice, it's built in. It drastically simplifies cipher negotiation. The list is cut down to just 5 strong, modern cipher suites, and they're all implicitly PFS-enabled.
Much less room for error.
Exactly. And crucially, it surgically removes dangerous legacy features that caused endless security headaches. Things like session renegotiation or TLS level compression. This simplification dramatically reduces the risk of misconfiguration from human error, which historically has been a massive attack vector.
Right. But reality check. Many organizations still have compatibility issues. Older enterprise clients, legacy systems, meaning TLS 1.2 configuration is still necessary sometimes, at least for a transition period. How should admins approach cipher selection in that TLS 1.2 world? What should they prioritize?
Okay, the essential tool here for operations is the OpenCipher Ciphers FV command. It lets admins test and verify exactly which suites are supported by their chosen configuration string, and importantly, in what order of preference. The absolute requirement is rigorous prioritization. You must explicitly exclude weak ciphers, anything 40-bit or 56-bit total junk, and all the known insecure ones like RC4 and 3DES. Get rid of them.
So what are the modern secure suites we should be explicitly enabling and putting first in the list?
You absolutely want to prioritize authenticated encryption with associated data, or AEAD suites. Specifically, we're talking about AES GCM and Checho 20 Poly 305.
Okay. Why AED?
They are fundamentally superior to older modes like CBC because they integrate integrity checking right into the encryption process itself. This dramatically improves security. It prevents attacks of padding oracles, which plagued older CBC implementations. Those attacks worked because the system could be tricked into revealing secrets based on error messages about whether the padding was valid or not.
Right, I remember those. Nasty.
Yeah. By using AEAD, you guarantee both confidentiality and integrity together in one go, much safer.
Okay, if we look at the key exchange side of things for TLS 1.2, what are the current recommendations for, say, asymmetric key strength and the mechanisms themselves?
Right. For asymmetric keys, the absolute minimum safe size for RSA today is 2048-bit. But really, if you want to achieve what's considered 128-bit cryptographic strength equivalence, the modern target, you need to be using 3272-bit RSA keys.
2D72 minimum for 128-bit strength.
Okay. But even more critically, the older RSA key exchange mechanisms, they're now generally considered insufficient, fundamentally because they lack forward secrecy.
Oh, we must be using ephemeral methods like ETDHE, even in TLS 1.2.
You absolutely must use them. Ephemeral Diffie-Hellman, and specifically elliptic curve Diffie-Hellman ephemeral, ECDHE, is strongly preferred. It's faster, stronger, and inherently provides that crucial, perfect forward secrecy. And now, of course, with OpenSSL 3.5, those new hybrid PQC algorithms like X25519, MLKM768 are also starting to appear as best practice options where supported.
And for the bulk encryption itself.
Stick only to those AEAD algorithms we mentioned, AES, GCM, and CHACH20 poly through hour 5. CBC mode is really being phased out precisely because of those security risks, unless you're using a very specific, rarely supported extension called Encrypt Then MA, and both the client and server implement it perfectly, which is just a huge operational complexity most people should avoid. Stick to AED.
Okay. The compromise of a private key, as we saw vividly with Heartbleed, is the ultimate nightmare scenario. Game over. What security mitigation actions should organizations be taking for really effective key management?
Right. The primary action is defense in depth for those keys. First, you need to understand the difference between protecting keys in transit or at rest versus protecting them in production memory. Passphrases are vital, yes, but they really only protect keys when they're stored off the production systems, like in encrypted backups or offline storage. Once that key is loaded into the memory of a running production server, a skilled attacker with root access can potentially retrieve it. So, for true security on production servers, especially with high-value keys or strict compliance needs, the only really robust solution is investing in hardware security modules, or HSMs.
The hardware boxes.
Yeah, these are specialized, tamper-resistant hardware devices. They're designed to make extracting the private key physically or cryptographically impossible because the key itself never actually leaves the secure chip boundary. All crypto operations happen inside the HSM.
Okay, so HSMs for ultimate protection. But beyond that, aggressive rotation is also key.
Absolutely vital. Organizations need to drastically shorten certificate lifetimes. We need to move away from those old 2 or 3 year certificates down to 90 days or even less. Let's Encrypt really push the industry here.
Right.
And perhaps even more importantly, rotate the keys frequently. Ideally, you should generate a completely new private key every single time you renew a certificate.
Don't just renew the cert on the old key.
Exactly. Don't just get a new cert for the old key. Generate a fresh key pair each time. This practice maximizes security by limiting the exposure window if a key ever does get compromised. It also reduces reliance on complex and often flawed key revocation checking systems.
Good point. Okay, finally, legacy protocol complexity. We saw how the Heartbeat extension led to Heartbleed. What about compression, TLS compression?
Disable it. Just disable TLS compression entirely. This is the specific mitigation against the crime attack. That attack allowed attackers to decrypt things like session cookies or authentication tokens by cleverly observing the size changes of the compressed data stream as they injected chosen plaintext.
Right.
And furthermore, you also have to be really cautious about compression that might be implemented at the application level because that can expose systems to the related breach attack risk. The overarching rule is pretty clear. Complexity and optional legacy protocol features are operational liabilities. They need to be stripped out for better security. And TLS 1.3 makes this easy by just removing support for TLS level compression completely.
Wow. Okay, so this deep dive really shows that OpenSSL isn't some static library you just install and forget. It's a continuously evolving living piece of global infrastructure. That strategic pivot to OpenSSL 3.0 brought essential stability and modularity with the provider system, right? Getting rid of legacy risks by default.
Mm-hmm.
And now version 3.5 is providing that crucial future-proofing with the integration of post-quantum cryptography.
Yeah, and the lessons from history, from Heartbleed's catastrophic memory leak, which really drove PFS adoption, to that Debian weak key mess exposing supply chain fragility, they all reinforce one non-negotiable principle. Constant operational vigilance is absolutely required. Configuration has to rigorously prioritize ephemeral key exchange, AEAD encryption, and sophisticated key protection, whether that's HSMs or just really aggressive rotation policies.
So for you, the listener, this knowledge has to translate into immediate action. You really need to check your cryptographic foundation starting today.
Right. First step. Run OpenSSL version A on your key systems. Verify exactly what version you're running and, importantly, what cryptographic options it was compiled with.
Okay.
Second, conduct a full inventory of your cryptographic assets. Where are your critical signing keys? Which systems rely on those potentially hidden statically linked OpenSSL libraries? You need that visibility. And finally, you must begin testing OpenSSL 3.5's hybrid PQC features now. The NIST timeline is fixed. 2035 is the final deadline for transitioning away from vulnerable crypto. Your organization needs to build true crypto agility into its processes, its testing, its deployments, starting today to meet that mandate. It takes time.
Crypto agility. It's not some future concept anymore, is it? It's fundamental resilience for today. And this leads us to our final provocative thought.
Yeah, consider this. If your organization's most sensitive, long-lived data, think trade secrets, personal health records, critical intellectual property, if that data was harvested today, encrypted only with classical crypto like RSA 2048, how many decades into the future would that data truly remain confidential before Q-Day arrives, and it can potentially be decrypted? The transition to quantum-safe cryptography isn't some distant research goal. It's a present-day operational mandate, and it directly determines whether the confidentiality of your current data has a lifespan measured in months, years, or decades.
That's definitely a timeline you can't afford to ignore. And that's all the time we have for this deep dive into the world of OpenSSL.